Welcome to Lecture 25A, entitled Introduction to Applying the Divergence Theorem and Stokes Theorem in 3D. So this series of 3 lectures, that's 25A, B, and C, come from the introductory part of Reading Assignment 5. And so this is going to be quite new material because you're going to be asked to synthesize a number of things that you've learned over the past couple of weeks, which means contour integration, surface integration, volume integration, and the application of the divergence theorem and Stokes theorem, specifically oriented to a certain class of problems. In particular, we're going to use the electromagnetics application area to demonstrate how Stokes theorem and divergence theorem can be applied to compute vector fields of interest. You might find this very useful in preparation for the course you take next term, that's ECE 221S, which is a course on electric and magnetic fields. So, as I mentioned, the material is more or less from the introduction to Section 2, parts of Section 2.1 and Section 2.3 of Reading Assignment 5. And the objectives of this particular lecture are understand the classes of vector fields that can be solved, also giving you some ability to understand how you can sketch irrotational and source-free vector field. Then next item would be the divergence theorem for irrotational fields problems, and basically under what circumstances we can use it, particularly when there's a high degree of symmetry. And lastly, Stokes theorem for source-free field problems, and again, under certain conditions, we can apply the Stokes theorem, that is when a high degree of symmetry exists. So main concepts, definitions, visualization skills, including sketching fields, units, and definitions. As usual, the second slide basically gives a summary of the slides to follow, so we'll just move on. All right, since this more or less now coincides with reading week, and we're going to make this very large change in direction, I thought I'd give you a bit of a roadmap here as to what is going to take place over reading week and the following 2 weeks. And so the main thing is going to topic will be the application of the divergence theorem and Stokes theorem. These are deliverables. And particularly, these are the sections of Reading Assignment 5 that you really should focus on. And then I'll get into more details shortly. So Section 2.4, Principles of Superposition. Some of this material is in a tutorial. We'll discuss that shortly. And then Reading Assignment 5, Section 3.5 and 4.6. That basically is where we apply the superposition to divergence and Stokes theorem problems. So the objectives over reading week and the following 2 weeks, I basically structured it in the form of a table with 2 columns. The videos and reading assignments to review. More or less, it's everything within Reading Assignment 5 where certain parts have been excluded, and the online tutorial videos. So as far as the specific sections are concerned, introduction in Section 2, introduction to Section 3 and Section 3.2, and review of the geometry will be tested on in Quiz 6, and you can refer to Table 4 in MAT291 schedule to figure out which is the one that you really ought to look at, aside from what we're going to be doing in the lectures. Also, the introduction to Section 4 and Section 4.2. You will not be tested on that, but in an exam setting, there will be a question coming from Section 4.2. And lastly, just going through videos 9, 10, and 11. So during reading week, basically prepare a list of questions for your TAs so they're ready for the tutorial Q&A session the week after reading week. And similarly for lectures, prepare a list of questions for your instructors so that they're ready for the lecture Q&A the week after reading week. All right, this is just a sort of the directory showing everything associated with Reading Assignment 5. And the part that I've aligned, that highlighted in yellow, is really the only document you're responsible for. Everything else there is more or less for your interest, except perhaps you want to make reference to the solution to the embedded problems in Reading Assignment 5, particularly divergence problem solutions here and Stokes problem solutions here. Everything else here is for your interest only, but these two and this one are more or less the primary sources that you should refer to. All right, so just let's go through a sort of a brief summary of the contents of Lecture 25A and your responsibilities. This actually goes beyond Lecture 25A, so really it's all of Lecture 25, that's A, B, and C, but I've just sort of put it in one location here. So in terms of the introduction and Section 2, these are more or less this is more or less the material we'll be covering in this lecture, Lecture 25B and 25C. You can see basically the page references and the parts that you should look over. It's about 20 pages, but a lot of it is just diagrams, figures, not that much math, mostly trying to give you an intuitive understanding of where we're headed. The main topic areas would be the sketching of the rotational fields and sorcery fields. And you need to go to section 2.31 and 2.3.2. But this will be covered in tutorial, but you should read through this material on your own. I made some reference to this in the material that's coming, but on a sort of very limited basis. The next thing will be the role of superposition and Dirac delta distributions. And so just as a general guideline, the principle of superimposing fields and solving a large problem as a set of subproblems is covered in section 2.4. All right, just a reminder, this material will be covered in a tutorial, but students should read through this material on their own. Students should also become familiar with doing Dirac delta distribution calculations, which will also be covered in a tutorial and also in the subsequent lecture, Lecture 25B, to a limited extent. And some of this material will be covered in some of the lectures to follow. So it'll be showing up over and over again. But in terms of understanding the basics, we'll do it in this lecture, but the tutorial has more information. And then getting into the application field, that's the irrotational and source-free examples. During the lectures, we will cover section 3.2, a problem similar to question 8 in section 3.5, sections 4.2 and 4.3, and a problem similar to question 7 in section 4.6. Students should also look at other examples in sections 3 and 4, since you will be tested on one of these geometries. In particular, see Table 3 in the MAT291 schedule document for the geometry that your tutorial section will cover, and Table 4 for the geometry you will be tested on in Quiz 6. All of the tutorial, basically, videos are available. And so for future reference, particularly during an exam, you can look at what other tutorials, what other sections covered in their specific tutorial. All right, so let's get on to the main topic then, and that is computing a vector field F when the curl of a vector field and the divergence of the field are given. In other words, in a typical application environment, this may be one of the scenarios which that you're given, and that the curl is known and the divergence is known, but you're not interested in curl and divergence, you're interested in computing the vector field F. So we basically now make reference to the Helmholtz equation, where we said that any vector field is basically the superposition of an irrotational field and a source-free field. So phi, basically the scalar potential, minus the grad phi, is just associated with a irrotational field, and the curl of A, which is a vector potential, is with reference to the source-free field. So the next thing we do is to take the curl and divergence of the vector field F. So if I take the curl of the vector field F and apply it to the gradient of the scalar potential and the curl of the vector potential, then I end up with a final result of curl of a vector potential A. And don't forget that the curl of the gradient of phi was equal to 0. And I'm going to call the curl of an A J. I'm just going to give it an arbitrary symbol, a vector J. And if we look at the divergence of the vector field, then I'll end up with minus the divergence of the grad phi plus the divergence of the curl of a vector field. But the divergence of the curl of a vector field equals 0, and so we're just left with minus the divergence of grad phi. But that's nothing more than minus the Laplacian of the scalar function phi, which is a scalar, so we're going to give it a label rho. And so if we put everything in a more compressed form, then we're looking at this as being the final set of expressions right here. And so typically in a physical problem, this is a given and this is a given. And so the question then is, well, how do we compute the field F? And if we compute the field F, are we guaranteed that there's only one solution? Okay, so again, I'm just stating it. There's more material in the notes, but you're not basically responsible for it. Most of it is buried in appendices. Uniqueness of solutions is guaranteed if rho and j decay at a fast enough rate when approaching infinity, infinity being the boundary. This situation occurs in practice. On the other hand, boundaries at a finite distance can also be considered, but this is outside the scope of this course. That requires a little bit more detail, and again, it's buried in the appendices, but you're not responsible for it. So the basic problem statement becomes one of, given rho and j, compute F. That's the problem, okay? However, in its current form, even this is a difficult problem to solve, but of course, we're going to be looking at problems where there's a high degree of symmetry, and under those circumstances, it turns out it actually becomes a manageable problem. All right, so the class of vector fields that will be solved. So the method we will develop to solve for F, the vector field F, can't be employed for the general coupled vector equation stated on the previous slide. So if the problem exhibits a high degree of symmetry, we will basically get into what we mean by that shortly, and the field is either circulation-free or source-free, then it is relatively easy to compute the vector field F. So the two cases we will consider are this irrotational field, where the divergence of F is non-zero, but the curl of the field is zero. So this is one example case that we'll look at. The second case is where the divergence of the field is zero, but the curl of F exists and is some vector flux density. This is a source-free field. All right, just a very sort of quick note here. We're beginning to run out of symbols. So at various points in these notes, the same symbols may be used to describe a different physical property. So we will use the symbol r to describe the radius in spherical coordinates instead of rho, to avoid confusion with charge density, which we will designate as rho. J is used to describe a current flux density, but it can represent a general vector field in other cases. So just keep in mind that symbols can be used in different contexts, but we'll try to be clear and stick with one set of symbols when we go through this material. All right, so what is the solution approach accounting for a high degree of symmetry? All right, so more or less what we're doing is describing the conditions in which we can state we have high degree of symmetry. So in an appropriate coordinate system, so for instance, we talked about cylindrical coordinates, spherical coordinates, planar, and so on, the vector field F satisfies the following conditions. The vector F has a magnitude which is a function of only one variable. So if it were x, y, and z, it would be only a function of x, for example. The vector F has a direction vector aligned with only one of the unit basis vectors. So again, keeping to a Cartesian system, I could say that the vector F only points in the y direction, a specific direction. Okay, that's it. I mean, it could also be, at some angle, right? But you can always basically derive new basis vectors if you want to, but nevertheless, it's just one particular direction. All right, so the two different approaches taken to solving these problems, given that we have a symmetry, one is the integral formulation and one is the partial differential equation formulation. For the integral formulation, under the conditions stated above, it is possible to apply the divergence theorem or Stokes theorem to convert the following equations into an integral form. So starting with basically an irrotational field, we have the divergence of F being the scalar density and the curl being zero. This is the divergence theorem now that we would apply to basically compute F given rho. In the case of a source-free field, the divergence F is zero, but the curl of F is given. So in this case, we can use Stokes' theorem to basically compute the value of the vector field F. So this is basically what we're going to do. So one section we'll deal with this class of problems. One section of the reading assignment will deal with this class of problems. For partial differential equation formulation, we solve a partial differential equation for the scalar potential phi and a partial differential equation for the vector potential A. but choose the appropriate coordinate system that reflects the problem's symmetry. The partial differential equation calculation would be performed in the transformed coordinate system. So we'll be solving something in cylindrical coordinates or spherical coordinates or toroidal coordinates, whatever the case may be. The results from reading assignment 4, objective 4, could be exploited for this purpose. However, basically, this is something that's you could look at, but you're not responsible for. So let's summarize the objectives and your responsibilities with regard to this reading assignment. In these notes, we will focus on the integral formulation. The differential formulation is not considered, but is reviewed to some extent in the context of optional questions in chapters 5 and 6 of reading assignment 5. You'll not be responsible for the differential formulation, but you'll find it useful to refer to this material in the ECE 221S course next term. All right, so now let's look a little bit about sketching of fields, because this is going to be very important as a sort of a starting point in solving problems. So we look at the two classes of problems that we basically already discussed briefly, and that is a rotational field and a sorcery field. So just some general basic guidelines. For an irrotational field, the vector field lines diverge from or converge to the source. Outwards if the scalar density rho is positive, and inwards if the scalar density rho is negative. Each differential element of the source can be considered as a point source. So for instance, if you had a volume with a certain charge density in terms of coulombs per cubic meter, then you could basically say that volume charge density basically is a sum of an infinite number of point sources. And so we can use the notion of a point source to basically establish what the field pattern would look like, and then by just doing a summation, which is a form of integration, we're able to achieve the total field for the full volume distribution. All right, the field pattern for a point source is a series of lines spreading out radially from the source, and the total field at a given point is a superposition of the field lines from all of the differential sources. So here I've just described in a very simple way in terms of how you can sort of imagine what the fields would look like, starting with something relatively simple. For the sorcery field, the direction of the flux density J at a given point, from a geometrical standpoint, is akin to the direction of a localized axis of rotation. Previously, we talked only in terms of geometry, but here now, we're essentially saying that the axis of rotation is synonymous with the direction of J, which is a physical property. The direction of the field F is determined using the right-hand rule. That means the thumb points along the axis of rotation, that's in the direction of J, and the vector field F forms closed contours in the direction in which the fingers point. Thirdly, the vector field F forms closed contours since the field is source-free. Divergence of F equals 0, which means fields basically cannot emanate from a point or converge to a point. So that means they have to form closed loops. And lastly, the divergence of the curl of a vector field we know is 0. But the curl of a vector field is J, and therefore the divergence of J is equal to 0. That also means that the vector field J has to form closed loops. And that makes sense because we always talk about a current has to flow through a loop. And a loop means a closed contour. And so when you draw J, you always have to assume there's a return path. This particularly the case when you're dealing with geometries which appear to be infinite in length. So a general note, regions where the vector field lines are straight, parallel to each other, and spaced equidistantly are regions where the field is uniform. Regions where the density of field lines increases in a particular direction are where the intensity of the field is increasing. So let's take two examples. This is field lines for an irrotational field. This is just showing the sketch without getting into details. So you'll notice here we have a source. It's a positive charge. And we have another source, which is a negative charge. Here the source lines are moving outwards. Why? Because rho is positive. Here they're coming in because rho is negative. So you can see the lines basically all start at a point and finish at a point. In this particular case, the positive lines basically are terminated at the minus. If this were only a positive charge, then these field lines would go out in a radial fashion to infinity. So this is an example, essentially, how field lines can be sketched. So just two notes here. The displacement field lines bunching implies a strengthening field. So you can see here they're getting tighter and tighter, which means as you move inwards here or out inwards, fields are getting stronger. So here, for instance, going inwards, they're getting denser. Out here, they're getting further and further apart, which means the field is getting weaker. All right, what about a sorcery field? In a sorcery field, the field lines form closed loops. And so, for instance, this would be the magnetic field for the Earth, and you can see the field lines coming in. Of course, it goes through the Earth and comes out the other side and then returns and comes back. So these are the individual field lines, again, all forming closed loops. The magnetic field bunching like this means the fields are getting stronger. And again, field lines form closed loops. So that's how you distinguish between a sorcery field and an irrotational field. All right, quickly, units and definitions review. Contour integration, differential arc length is ds with a bar. Surface area integration, differential surface area vector at a given point on an arbitrarily shaped surface is ds with the bar. Terminology, use the terminology dA instead of ds if the differential surface area in 3D is planar. If it's 2D, then we don't recognize this as an oriented surface, so it just becomes a scalar differential. Vector notations. Vectors are sometimes written in bold rather than with an arrow over top. So ds with an arrow over top is equivalent to ds bold. dA with an arrow over top is equivalent to dA bold. And ds with an arrow over top is equivalent to ds bold. Alternatively, we can write ds is equal to tds, ds is equal to nda, and ds is equal to nsda. All right, and then densities. There are two types of densities to consider. We will differentiate the term scalar density rho and flux density j. The scalar density rho is a scalar value function, whereas the flux density j is a vector valued function. The scalar valued function rho and the vector valued function j can be either continuous, discontinuous, or incorporate Dirac delta distributions to represent point, line, or filaments, planar sheets, or curved sheet sources. Dirac delta distributions will be basically discussed shortly, namely in the next lecture. All right, scalar density rho, just the different units, type of distribution, the symbol, and the unit. So if it's a volume distribution, it involves rho, which means coulombs per cubic meters. If the charge is distributed over surface, then the surface charge density is coulombs per meter squared. If it's distributed over line, either in 2D or 3D, then the charge density would be coulombs per meter. And if it's distributed over a single point, and the charge basically would be just straight coulombs in 2D or 3D. Now, I've chosen basically electrostatics example, but it could also be a calculation involving mass. So in that case, basically, the unit of charge C is replaced by the unit of mass, which is kilograms. All right, what about flux density J? So we can have a volume current, a surface current, and a line current. A volume current would be just if I had to say a copper conductor, and I have a current flowing through the copper in a specific direction. So that would be a volume current distribution. And J, of course, would be directed. The units of the current flux density under those circumstances would be amps per meter squared, but amps is also coulombs per second, so you could also write it as coulombs per second per meter squared. If it's a current that just runs around the surface, then the current have units of amps per meter, and if it's a line current that's physically moving through a filament, then the units of current through the filament are basically the current in units of amps. And we'll be using specific symbols to refer to either volume current distribution, a surface current distribution, or line current distribution. Again, we don't necessarily have to be working with charge here. We'd be good using mass, in which case the units would become kilograms. All right, so what are the tractable cases that can be solved without specialized tools or knowledge? An irrotational field F and a high degree of symmetry for rho, right, which means that we have only the divergence of F equals rho to compute, and we do that with the divergence theorem. And so here it basically shows this is the integration over a closed surface. This is the divergence over a volume, but the divergence of volume from here is rho. So if we know this, we can compute the right-hand side. And now we have to figure out how to get f out of this, in which case we can compute what f is. This can only be done if we have a high degree of symmetry. For the case of a source-free field and a high degree of symmetry, for J, we would basically be dealing with the solution to the curl of f equals J, the vector J. So we compute that with Stokes' theorem. So for Stokes' theorem, you would have basically a closed contour integral is equal to the curl of the vector field integrated over an open surface that's bounded by the contour. But curl of f is J. And so if we know what this is, we can compute the right-hand side. And so now the trick is to somehow get f out of here so that we can compute its value. And so if there's a high degree of symmetry, then basically this side becomes relatively straightforward to compute. This is going to be easy to compute, but tricky because it really, the difficulty will depend on the type of current distributions that you're dealing with. Well, that concludes Lecture 25A. Thank you for listening.